This is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to talk about electromagnetic waves, and we'll begin the discussion with the simplest kind of wave you encounter in electromagnetism, and that is a plane wave. Let's begin with Maxwell's equations. Now we're going to be interested in a source-free region of space, so therefore we're going to only deal with the source-free Maxwell's equations. So the right-hand side of Gauss's law becomes zero. Divergence of the magnetic field is still zero because, of course, no magnetic monopoles have ever been observed. Faraday's law is the curl of the electric field is equal to minus the time derivative of the magnetic field. No change there. And then for the Maxwell Ampere's law, we have the curl of the magnetic field is equal to the displacement current times mu naught plus current. Since we're dealing with source free, that last term is assumed to be zero. Okay, so let's go ahead and take the curl of the electric field. I can use one of those vector identities. The curl of a vector is equal to the gradient of the divergence of the vector minus the Laplacian of the vector. And that's equal to, we transpose the time derivative and the curl we have minus time derivative of curl V. Okay, well, by assumption, the divergence of the electric field vanishes. We're dealing with the source-free region in space, so therefore the charge density, free charge density, is going to be equal to zero. Over here, let's see, we got minus, so get rid of that. That's just the Laplacian of the electric field. And the curl of the magnetic field by the Ampere-Maxwell relation is equal to mu naught epsilon naught. And then we've got two time derivatives, or second derivative, I should say, of the electric field with respect to time. I can go through the same procedure with the magnetic field and wind up the Laplacian of the magnetic field is equal to mu naught epsilon naught second derivative of the magnetic field with respect to time. Now, mu naught epsilon naught, of course, has a very special value. That's equal to 1 over c squared, where c is the speed of light. Equations that have this form are wave equations. Before I get into looking at the wave equations, it's useful to consider a scalar wave equation. First of all, because after all, you've only got one component to deal with. So therefore, let's consider the Laplacian of some scalar function psi, and that's equal to 1 over v squared second derivative of psi with respect to time. So psi is just some arbitrary function that satisfies the wave equation. The most general solution and we'll assume that our wave is propagating in the z direction, is equal to f times z minus vt plus g times z plus vt. So generally speaking, this psi is a solution, or rather the solution psi is the form of a forward traveling wave. And a backwards traveling wave. One possible solution to the wave equation is equal to A cosine k z minus vt plus some constant. Solutions of this form should be familiar to you from general physics, but we'll go ahead and write down what each of these terms, factors, or whatever means. So A, of course, is just the amplitude. The quantity, the argument inside cosine is just phase. K is equal to the wave number. And it's related to the wavelength lambda via this relation. Lambda is equal to 2 pi over k. V, of course, is just the speed of the wave. Delta is equal to the phase constant. Period of the wave is just equal to 2 pi over kV. Okay, so we also have frequency. And I'm using the Greek letter nu to represent frequency. You know, back from physics class, of course, you most likely use lowercase f. And that's just equal to 1 over the period, which is just equal to kV over 2 pi. And it's useful to introduce omega, which is the angular frequency. And that's equal to 2 pi mu. Therefore, I can rewrite the phase as kz will just still be kz, but then the second term will actually be equal to minus omega times time. Plus our phase constant. Now, trigonometric functions can be awkward to work with. The exponentials are certainly easier. So why don't we make use of the Euler formula? Which tells us that e to the I theta is equal to cosine theta plus I sine theta. And convert this to a complex function. Use a tilde to indicate that a quantity is complex. So there we have our complex function, f is equal to a times e to the I kz minus omega t plus delta. Now, oftentimes it's useful to combine this constant term, combine all the constant factors together. So we'll go ahead and replace the amplitude a by a tilde defined as a times e to the I delta. So this, we put a delta up here, and then we remove this one. So basically we're just kind of absorbing the constant into the amplitude a. Now, by convention, we assume that the physical content is in the real part of this function. So therefore we get our wave solution there, and what the real physical solution is, we just take the real part. Okay, so solutions in this form called plane waves. So to get an idea or better conceptualize what that means, let's go ahead and look at a simulation. In this simulation, we imagine that the region of interest is infinite in extent. For the present, we are not concerned with where the waves came from, and we don't consider boundaries. The definition of a plane wave is a wave the phase of which is the same in a plane perpendicular to some given direction. The solution we just derived satisfies this definition. The gold arrow points in the propagation direction. The red line indicates the vector r from the origin to some point on the plane. Another way of expressing this definition is that a plane wave is a function only of the perpendicular distance from the origin to the plane. So the fields are uniform everywhere on this plane. If the plane wave propagates in the z direction, then the plane wave is a function only of z. There is no x or y dependence. In this next simulation, we see a wavefront at several points in time. Once again, the gold arrow indicates the direction of propagation. Now that we've looked at what plane waves look like, let's take a look at electromagnetic plane waves. Maxwell's equations impose additional constraints because remember, not only do these solutions have to satisfy the wave equation, they also have to satisfy Maxwell's equations as well. Unfortunately, I just erased them, so let me rewrite these on the board. Consider electromagnetic waves that propagate in the z direction. tilde indicates we're talking about complex quantities. We're doing that because it's a lot easier to work with exponentials than trigonometric functions. Also, even though this function or the solution is only a function of z, this vector quantity can have components in the x, y, and z directions. Let's take a look at what constraint delta E imposes. Or I should say the divergence of E imposes. Well, our solutions here are only functions of z, only functions of the direction of propagation. So therefore, if I take the partial derivative with respect to x or the partial derivative with respect to y, I get 0. So that part of the equation is automatically satisfied. However, this does depend on z. So if I take the partial derivative of this with respect to z, I'm going to wind up with an ik times e naught tilde, z component of that's equal to 0. So k is a wave number, that's not going to vanish. And therefore, that tells you that the z component of the solution must be equal to 0. So it only has x and y components. If I do the same kind of analysis on the magnetic field, that implies likewise that the z component of the magnetic field is equal to 0. So what do you conclude here? The z components vanish and you only have components that are transverse to the direction of propagation. So therefore we conclude that electromagnetic waves in a vacuum are transverse. Now let's take a look at the curls. What kind of information does that give us? Well, if I take that, let's do the time derivative because that's a lot easier. Whenever you take the time derivative of any of these functions, that amounts to multiplying by minus I omega. We've already just determined that Ez tilde is going to be equal to 0. So do the rest of this, you look at the x components, well that's 0. This is going to be equal to minus a partial derivative with respect to z of the y component. And I'll be in the x direction. And if I look in the y direction, that will give me plus partial derivative with respect to z of the x component of the electric field. And when I take the partial derivative with respect to z, if I look at the solution here, that basically amounts to multiplying by ik. And we know that is equal to the minus partial derivative of b with respect to time. Therefore, we wind up with conclude that we have minus k times the y component of E naught tilde is equal to omega times x component of E naught tilde. And we also have k x component of E naught tilde is equal to omega y component of E naught tilde. And therefore, we conclude that B naught tilde, magnetic field, is related to the electric field by a k over omega times z direction, z unit vector, crossed into E naught. So, both of these electric and magnetic fields are perpendicular to the direction of propagation, but the magnetic field and the electric field are perpendicular to each other. So, the vectors k, e, and b form an orthogonal set. First of all, you choose the direction of propagation, and then you decide, well, which way is the electric field pointing, and then that determines what direction the magnetic field is pointing in. So let's take, for instance here, let's suppose that your electric field is pointing in the x direction, or I should say, yeah, pointing in the x direction. And therefore, magnetic field is going to point in the y direction. And to see the actual physical content by convention, we take the real parts. Again, it's useful at this point to look at a simulation to get an idea of what these, how these two waves behave, or these two components, I should say, behave with respect to each other. Here we see the electromagnetic wave traveling in the z direction. We'll take the electric field to be in the x direction, and the magnetic field will consequently be in the y direction. Electric field is indicated by purple, the magnetic field is indicated by green, and the direction of propagation is indicated by the gold arrow. The electric and magnetic fields are perpendicular to each other and are perpendicular to the direction of propagation. Electric and magnetic fields have the same frequency, and they are in phase. Okay, now that we've handled an electromagnetic wave that propagates in the z direction, let's consider how these equations have to be modified to handle the wave traveling in an arbitrary direction. Before, we had k was equal to wave number k in the z direction, but now it's in some arbitrary direction. So rewriting these two expressions. We've replaced the k, z, and the exponent by vector k dotted into the vector r. And also here, E, both the electric field and magnetic field, are functions of the vector r, rather than just z. Okay, so how do our constraints change? Well, it still will be the case that the partial derivative with respect to time is will essentially be the same thing as if I take minus I times omega and multiply it. Okay? Now what about the gradient? Because now we've got to consider all three directions, not just basically dependence on z, but possibility that you've got dependence on x, y, and z in some fashion. So essentially, delta is equivalent to operating, if you will, by ik. So therefore, our conditions now become k dotted into the electric field is equal to 0. Notice I'm writing a tilde over the top, and again, that's to emphasize that we are talking about complex quantities. And again, to get the real physical solution, we're going to take the real part of this. Okay, the other constraint, or similar constraint, is that k dot into magnetic field is equal to 0. So that's the divergence of E is equal to 0, the divergence of B is equal to 0. So these two together tell us that the electric and magnetic fields are perpendicular or transverse to the direction of propagation. Now what about the curls? So if I take the curl, that's equivalent to taking ik cross electric field. And that's equal to, we want to have minus partial derivative of b with respect to time, so that's equivalent to multiplying by minus I omega. So minus minus, we have I omega and b. Maxwell's law for source-free region of space becomes ik cross magnetic field is equal to u naught epsilon naught, and we've got partial derivative with respect to time, so that gives us minus I omega times electric field. Okay, and I'll just get rid of the i's here. And these are the constraints that an electromagnetic wave has to satisfy. Okay? And sometimes it's more useful if you are to, or maybe makes things a little bit clearer, if you replace omega over k by c. So that is the speed of the propagation. I'm just going to turn my attention to polarization. In general physics, you undoubtedly talk about two different kinds of polarization. One with longitudinal, and the other kind was transverse. An example of a longitudinal wave, well, that's a sound wave, and essentially what that means is that the displacement, or a better way, or I should say disturbance, but the better way of saying that is that the displacement from equilibrium is in the direction of propagation, so it's parallel to propagation. Transverse means that the disturbance or the displacement from the equilibrium is perpendicular to the direction of propagation. So, as we just saw, electromagnetic waves in a vacuum are transverse. And of course, longitudinal waves, or sound waves rather, are longitudinal waves. I want to look at some kinds of polarization with which you probably are not yet familiar. So, it is convenient to break this vector into its three components, to write it out explicitly. And you could write it as x, y, and z, but it's better just to leave those directions a little bit more general. So instead of that, I am going to write this as E naught p. Put a little p unit vector out in front, e to the I k dot r minus omega t, plus s unit vector the s component of the electric field, e to the I k dot r minus omega t, plus one final term. We'll have k caret component of the electric field, e to the I k dot r minus omega t. Now, we just determined that electromagnetic waves are transverse, so therefore this final term vanishes, and we're just left with these two other terms, and maybe p's in the x direction, maybe s's in the y direction, maybe some linear combination thereof. But why use this notation? Well, to be honest, at this stage of the game, I start getting a little bit irritated with the notation that the authors use. It's not because anybody's flouting convention. Everybody uses something a little bit different here. If you look at Wright's, if you look at Griffith's, you look at Heald, or any other book, the notation looks a little bit different there, and because people use the k's to represent different things. So in this case, I've mostly followed Griffith's notation, but here I'm diverging from his way of doing things a little bit because I'm breaking down this into P and S components. So what do I mean by P and S? Well, when we get into a discussion of waves impinging on an interface, it's useful to think about what part of that wave or what component of that wave is parallel to the plane of incidence and what component of the wave is perpendicular to the plane of incidence. So in that spirit, P represents parallel, and S is actually a German word, senkrecht, and that means perpendicular. So, S and P are certainly perpendicular to each other, and I'm going to go ahead and make the phase constant explicit, so I'll replace E naught tilde by E naught P, E to the I delta P. So basically this is giving us the phase in the plane of, parallel to the plane of incidence, and similarly for the S component, perpendicular component. Now the important thing here about these two phase constants is what's their difference? So I'm going to introduce a new constant delta, which is just the difference between these two. Furthermore, I can take delta S equal to 0 with loss of generality. Just basically specifies the origin of T. So therefore, we've got EP. And I'm going to go ahead and write this, go ahead and take the real part of it, so we are dealing with them physical way. We've got E naught P cosine K dot R minus omega T plus delta, and ES is equal to E naught S cosine K dot R minus omega T. So to investigate different kinds of polarization, it depends on basically what these values are related to each other and also what the phase is equal to. So I'm going to take, let's consider what's happening at the origin. Okay, so let's look at some examples here with this wave that has two components, one P component, one S component. They're perpendicular to each other. And of course, they're both perpendicular to the direction of propagation. Now let's see what happens when the phase constant takes certain values. And when E naught P and E naught S, when they have values equal to each other, and when they're not equal to each other. Let's first take the phase constant to be 0. Both components are proportional to cosine omega t. So the electric field always points in the same direction, E sub p in the p direction plus E sub s in the s direction. And its value ranges continuously from square root of EP squared plus ES squared to 0 to minus square root of EP squared plus ES squared. Polarization in this case is linear. Polarization will also be linear if either the P component or S component is 0, or if the phase constant is pi. Let's next take the phase constant to be pi over 2. So now the two components are out of phase, with the result that the electric field traces out an ellipse, and this is in the clockwise direction. This is called right-hand elliptical polarization. However, note that the right-hand rule does not apply. If we've taken the phase constant to be minus pi over 2, the electric field would trace out an ellipse in the counterclockwise direction and is called left-hand elliptical polarization. Notice once again, the gold arrow indicates the direction of propagation. If we impose the additional constraint that EP be equal to ES, we'll have circular polarization. The magnetic field has the same polarization as the electric field, only rotated by 90 degrees in the counterclockwise direction.